Over the next 18 minutes, I want to take you on a journey beyond Mars to the outermost planets of our solar system. And I want to undertake this journey to address an age-old question: is there life beyond Earth? And while I will not be able to answer this question with you today, what I can and will do is share an idea that this answer is probably not as far off as you might think. I firmly believe that within our own lifetimes, we have the capability to look for the signs of life in the ocean worlds of the outer solar system with existing technology. And I'll define what an ocean world is in a few minutes. My job, or more accurately, my passion, is to work with large groups of scientists and engineers to study and explore our solar system using unmanned spacecraft. And what I hope to do with you today is to share that passion and convince you that not only are there places with the potential to harbor life right here in our own solar system, but that we have the capability today to explore them. But I'd like to start our journey right here on Earth. So 70% of the Earth's surface is covered by oceans, but only a very small fraction of those oceans have been explored. And for the majority of the history of human exploration, the oceans have played a very similar role to the role that space plays today. They're where imaginations run wild, and the deepest and darkest parts of them are both unknown and unknowable. This started to change in about the mid-1800s when expeditions like the HMS Challenger started dredging up thousands of never-before-seen species in the Earth and showing us how diverse and rich life in the ocean was. But the general consensus was still that the ocean's deepest and darkest depths, where the sunlight doesn't shine, were barren wastelands devoid of life. But that all changed in 1977 when an expedition from the Woods Hole Oceanographic Institute was looking for a hydrothermal vent off the coast of Ecuador near a mid-ocean ridge. And while the vent itself was something that was predicted but not found yet, and they are credited with the discovery of hydrothermal vents, they also discovered a completely unknown fact that these hydrothermal vents support rich biota. They're teeming with life. The sun doesn't shine here, but these vents are teeming with life. And this result was so unexpected that that entire expedition did not have one biologist on the boat. Okay? And so they went back to this vent system 2 years later with biologists in order to study them, and also National Geographic came along and made a wonderful documentary called Dive to the Depths of Creation that you can watch in your own free time. But at the same time that we were studying the biology of these hydrothermal vent systems off the Galapagos Islands near Ecuador, the Voyager 1 spacecraft was obtaining the first high-resolution images of Jupiter's moon, Europa. And what Voyager found was that Europa had a young surface, advented by the fact that there's very few impact craters at all on the surface, and the surface is instead covered by these fracture patterns that create a jigsaw puzzle. Okay, they crisscross all over the surface, and they're formed as Europa orbits in 3.5 days around Jupiter, being pushed and pulled by Jupiter in an eccentric orbit. And if you look closely at the surface of Europa, you can actually reassemble this jigsaw puzzle in certain places. But perhaps the most astonishing discovery regarding Europa was the fact that underneath this icy crust is a liquid water ocean, a salty liquid water ocean that contains 3 times the amount of water in all of Earth's oceans combined. And this discovery was made by the Galileo spacecraft in the mid-1990s using its magnetometer instrument that noticed that the magnetic fields around Europa were changing. And the physics behind this discovery are very similar to the physics that caused you to be pulled out of the line the last time that you went through a metal detector at the airport. Okay, when TSA pulls you out of the line, they do so because when you go through that metal detector, you're going through a very rapidly changing magnetic field. And if you happen to have something conductive in your pocket, say you left your keys in your pocket, your keys are going to produce an induced field that'll set off the alarm. And in this case, the induced field created by a large liquid water ocean underneath Europa's crust set off the alarm to the Galileo spacecraft and informed us that 20 to 50 kilometers below this ice shell is a deep ocean that's 10 times deeper, about 100 kilometers deep, 10 times deeper than the Mariana Trench, the deepest part of Earth's oceans. Now, a few years after the discovery of the European Ocean, a different expedition, this time from the University of Washington's School of Oceanography, was looking off the mid-Atlantic ridge, and they found hydrothermal vent systems in a place where they never expected to find them. Okay? The vent systems near Ecuador are powered by hot magma. The vent systems found here off the mid-Atlantic ridge, known as the Lost City, are powered by chemical exothermic reactions, heat-producing chemical reactions between ocean water and rock. Okay? The process is called serpentinization, and the best analogy I can give you is the last time you went skiing and used a hand warmer, where you shake up the hand warmer and it creates heat. That's what's happening here. And the discovery of Lost City, it changed your understanding of the potential for habitability in the outer solar system. Because now, you don't need hot magma to power vent systems. You just need salty ocean water and rock, which means that it's very plausible for there to be vents like Lost City at the base of that European ocean. And in fact, NASA is trying to understand the open questions around Europa, such as, what is the habitability of that ocean? If the ocean is habitable, is there life there? And there'll be a mission launched in the mid-2020s to try and take the first steps towards addressing that question, to look at the composition of the shell of Europa, to look for organics, to look at how that ocean surface, though the ocean underneath, is interacting or communicating with that surface. And you also will be a Pathfinder mission towards developing the knowledge we need about Europa to go back with a drill through, and possibly put a submersible into that ocean. And even though that mission is decades off, we are already developing the technology needed to do that. Okay? But while we wait for that submersible to be built, I'd like to take you to the next of our targets, which is Saturn's moon, Enceladus. So Europa and Enceladus are both ocean worlds. And an ocean world is a body that has a substantial liquid ocean either on its surface or in its subsurface. And while there are many potential ocean worlds in our solar system, there are 4 that are currently incontrovertible. The first one is Earth. The second is Europa. The third is Enceladus. And the last, which we'll talk about in a few minutes, is Titan. So now Enceladus was also first imaged by the Voyager spacecraft. And similar to Europa, Voyager showed that there are large portions of Enceladus' surface devoid of impact craters. It's geologically active and it's young. But even before Voyager made it to the Saturn system, we knew Europa was interesting for 2 primary reasons. One, it just happens to sit right in the middle of a diffuse ring of Saturn. So Europa's right in the middle of Saturn's E-ring, and it also happens to be the brightest object in the solar system. Or more accurately, it's the most reflective object in the solar system. Enceladus has the reflectivity of freshly fallen snow. The next spacecraft to visit Enceladus after the Voyager missions was the Cassini-Huygens mission to Saturn, which redefined our understanding of the outer solar system. Cassini is still orbiting Saturn to this day, but made its first flyby of Enceladus in February of 2005. And when Cassini flew by Enceladus, its magnetometer team, the magnetometer instrument, saw field lines in the magnetic field around Enceladus that looked more like they belonged to a comet with a tail than a solid moon. And so that magnetometer team told the Cassini project, something's going on here. Next time we fly by this moon, let's get a little bit closer. Okay? And while that discussion was happening, the imaging team on Cassini was looking at the moon and seeing something going on in the southern portions. And they couldn't quite tell if there was something going on in Enceladus or if there was just some kind of noise or scattering in their instrument. And they were perhaps a little biased in the beginning because everything we knew about solar system formation said moons as small as Enceladus. Enceladus has a diameter of 500 kilometers. It would nicely fit between Los Angeles and San Francisco. Things this small have to be cold, dead objects. And another important point is that the cameras around Voyager, when they arrived in the Saturn system, there was no sunlight in the south. So we were seeing the south part of Enceladus for the first time. But when we made those second and third flybys in late 2005, everything changed and we found out just how wrong we were. When they got close to Enceladus, we found out that there were fractures called tiger stripes at the base of the southern part of the moon. And that these fracture patterns, they were hot, okay? They were about 60 or 70 Kelvin, 60 or 70 degrees hotter than the ice surrounding them. Something was generating heat. And coming out of them was both gaseous water vapor and particles of water ice in jets, more than 100 jets, that were feeding and generating Saturn's E-ring. And you can see some images of the jets there at the top. So now after this, there was about a 3-year hiatus while Cassini was orbiting other places in Saturn. And in 2008, it went back to Enceladus using a different instrument that looks at the composition of particles called a mass spectrometer. And what the mass spectrometer found was that the particles coming out of these jets were imbued with organics. Okay? So there was organics here. And this was a major discovery and caused a reprioritization of how we thought about icy satellites in the Saturn system and turned what were originally going to be 4 flybys, roughly 4 flybys of Enceladus by Cassini, to over 20, 7 of which went straight through this plume. About a year after the discovery of organics in these plumes, another instrument that also looks at composition investigated one of the larger ice grains. And what that instrument found was that mixed in with this ice were salts. And the only way for that to happen was if there were salts in solution to a large liquid body, and that these ice particles that are coming out of the plume, or these particles coming out of the plume, came out as liquid droplets and then froze in a process like a sea spray. Now, about this time, Cassini had been around the Saturn system long enough to build up integrative knowledge regarding the gravity and topography of Enceladus. And that data was analyzed to say that that liquid body that sourced these jets had to be a global subsurface ocean. And then the last discovery, the most recent one that I would like to share with you on Enceladus, was that in these particles, in this jet system, they also found nanophase silica grains. And these very, very tiny bits of mineral, the way they form is that you originally have minerals in solution of hot water. And as you cool that water, these little grains form and come out of solution. And so this is billed as evidence of lost city-like hydrothermal vents at the base of Enceladus's ocean, where you have hot water with these minerals mixed in, that as it cools and rises in the ocean, these minerals comes out as these nanophase silica grains. So now, if we make a list of the 5 things that you need to support terrestrial-based life, you would have liquid water, organics, energy, and chemical gradients, okay? And minerals. And Enceladus has all 5. And they're not hidden beneath an icy crust. They're spewing out into space in the form of these jets, creating a free sample for us to possibly fly through, and to do so with instruments designed to see if there's any evidence for life in these particles or in the Europa Ocean, or the Enceladus Ocean, I'm sorry. Now, and the answer to the question I posed in the very beginning, by the way, of why is Enceladus the brightest object? Well, it's actually spray painting itself white with these particles. Now, these particles are pervasive, and they get all around the Saturn system. And some of them actually end up in Saturn's largest moon, Titan. And Titan is the 4th ocean world that I'd like to talk with you about today. Titan is special. And in order to start this discussion, I want to try and help you visualize what it would be to be on the surface of Titan. And so, if I can ask you to think about a picturesque freshwater lake with lush green grass and leafy trees all around you. Maybe you're at a lakefront vacation this summer near my hometown of upstate New York in Ithaca. And as you're looking at this picturesque lake, you see a reflection on the mirror-smooth lake of clouds over by. It's about to rain. Now, if we let the grass and the vegetation disappear, and we turn the landscape into a more rocky landscape, similar to what you might find in the southwestern deserts of the southwestern United States, and then let the temperature drop to a bone-chilling, balmy minus 208 degrees Fahrenheit. Okay? The air gets a little bit denser. Okay? If there's little waves lapping on the beach, they start coming to you sharper in your ears. But you yourself feel lighter, courtesy of reduced gravity. And when you look back at that smooth lake surface and you see the clouds pass by overhead, you're now looking at a hazy orange sky with the brightness of early twilight. And after those clouds are gone, you finally start to see it rain. You start to feel the raindrops with large splashes hitting your hand, and you notice that they're larger than expected. They're bigger than raindrops you're used to seeing, and they're falling at a much slower rate. And the ground around you, it's not rock and dust and soil. It's broken up parts of water ice mixed with organics in the forms of plastic shavings and styrofoam beads. So if you can imagine all this, welcome to the surface of Saturn's moon Titan. And be careful, because there is no oxygen, so you have to be careful about breathing. But Titan is the largest satellite of Saturn, the second largest satellite in our solar system, and the only moon that has a substantial atmosphere. And it's actually a good thing that Titan's atmosphere is cold and dense, because at these temperatures and pressures, methane can flow like liquid water on the surface. And so Titan has a methane-based hydrological cycle that's completely analogous to the way the water cycle here on Earth works. And so the processes are very similar, and you end up with geologic structures on Titan that are strikingly similar to the ones we find here on Earth. On Titan, there are dunes, and those dunes have the same size and shape to the largest sand dunes that you'd find in the Namibian and sub-Saharan seas of Africa, sand seas of Africa. There are deposits at the ends of rivers and streams and landsides called alluvial fans and deltas. Okay? We find those on Titan, and they're very similar to the ones you might find in the Atacama deserts of Chile or Death Valley National Park here in the US. There are mountain chains that have very similar structure to the Himalayas of Southeastern Asia, and perhaps most astonishingly, there are lakes and seas that have coastal morphologies that are very, very similar to marine and freshwater lakes and seas that we see all around here on Earth. Yet, those dunes are not made of quartz or silica particles. They're made of organic particles, more like plastic. Those deposits at the end of rivers, those alluvial fans, are made up of broken water ice and organics. Those mountains are also made up of broken, dirty water ice, and those lakes and seas, well, they're filled with liquid hydrocarbon, methane and ethane, that's very similar to liquefied natural gas. Titan is a natural laboratory for studying the processes that shape Earth and perhaps even the fundamental limitations of life. You cannot help but ask whether or not some exotic form of life may have developed in these hydrocarbon lakes and seas. The fundamental requirements for life, organics, liquid, and energy, all three are here. And as it was put in a 2007 study by the National Research Council, the seas of Titan are a test of the universality of life as a basic response to cosmic evolution. Now, Titan is actually a world of two oceans. You have these hydrocarbon seas on the surface, but then about 100 kilometers below the icy crust, there is a second ocean, a subsurface liquid water ocean, which recent evidence suggests may actually be salty and have direct contact with rock. But in terms of accessibility, it would be a lot easier to access these surface hydrocarbon seas than drill through 100 kilometers of ice. So perhaps the next mission to Titan could be an extraterrestrial boat to land in one of these seas and look for evidence of molecular patterns or structures that deviate from the randomness of abiotic chemistry and show signs of something else going on. And so, in summary, I think it's safe to say that we live in truly extraordinary times. And I hope that I've convinced you that whether it be a submarine into a European ocean, or a spacecraft flying through the plumes of Enceladus, or a boat landing in a sea of Titan on its surface, that we have the capability to look for signs of life in our own solar system, in the ocean worlds of the outer solar system. And we have the capability, all we need is the will in order to move forward and progress past these recent discoveries and move on to these next discoveries in spacecraft. And I'd like to close with a final thought that in the past, explorers had to go off and then they come back years later to relate their findings to everybody. But in the advent of the digital age, missions like the Mars Exploration Rovers stream back their data at the same time to both the mission scientists and to everybody else. And so everybody shares in this exploration together. And so I look forward to sharing the exploration of the outer solar system with you, and thank you for your time.